seems like everyone's here now. So today I'm going to talk about something that I think most people in this conference are not very familiar with. But basically, first of all, I would like to introduce a little bit organic soil cells. So that's the main topic that we work on in my laboratory at the University of Electrocommunications in Tokyo. And before anything else, I would like to emphasize the importance of solar energy and soil cells, and especially in these kind of low-income countries, because solar energy is actually a renewable energy that's available pretty much everywhere, and it's most abundant in these sub-Saharan countries, and also in Australia or in South Africa, for example. But these guys here are probably the ones that need it the most, because through these kind of free renewable energy, they would get access to better health, education, and in general quality of living. But when we look at the same world map, but not in terms of solar irradiation, but in terms of photovoltaic capacity, you see that in this region of the world, there's almost no solar capacity. So there's a need for new low-cost photovoltaic technologies. And organic soil cells are just that. So basically, unlike the conventional silicon soil cells that require high energy, so usually temperatures above 1,400 degrees, but also costly materials and costly equipment, and actually very strict conditions. So no space for impurities when you make silicon soil cells, especially crystalline silicon soil cells. In contrast with these kind of conventional soil cells here, you have organic soil cells that you can make with a very low temperature processing. You can use relatively cheap materials and low-cost equipment, such as spray coating that you generally use for painting your car. You can use an inkjet printer like the one you probably have in your office. You can also use roll-to-roll printing to print your soil cells like newspaper, basically. And the research level, what's used the most probably is spin coating here, which you might be familiar with if you've ever worked with photoresists for microlithography, for example, or nanolithography. So these organic soil cells, they also present other advantages with respect to conventional soil cells. One of them is that they're very lightweight. They're semi-transparent, so you can make photovoltaic windows like the one here. This is something we made in my laboratory, so you can see that if you compare it to a regular window, the transparency is slightly lower. So you have 70% of transparency in case of regular windows, but in the case of photovoltaic windows, you have around 40%. But in exchange for this 30% loss of transparency, you can gain in terms of solar capacity. So you get around 40 watts per square meter. So imagine if you basically change all the windows of your high buildings, especially in Tokyo, there's a lot of them. If you exchange all the regular windows for photovoltaic windows, you'll get a large amount of or large capacity for producing electrical power. The other thing is that they're flexible, so you can integrate them into a variety of designs. So you can see here at the bottom right part, there's a next generation sports car that's fully powered by organic soil cells in the windshield here. So this is a concept car made by Nissan. It's called Nissan IV. Some European companies are making these kind of solar trees, so you can integrate your solar cells into urban infrastructures, basically, or into wearable electronics like portable chargers or chargers integrated into your wearable or your jackets or anything like this. So it's a technology that has a great potential. Recently, so this I was really proud of it, but like 5 years ago, I made one of the first organic soil cells with a power conversion efficiency over 10%. Right now, the efficiency has reached around 18%. But the major drawback of these organic soil cells is their limited durability. So usually they don't work anymore after 5 years. And that's like the main issue that they're facing right now to get to large-scale commercialization, let's say. Of course, if you think about these kind of technologies here, they don't need to have a lifetime over 5 years, but the problem is that if you use organic soil cells in these kind of technologies, after less than 5 years, you will just throw everything away and it will become electronic waste. So what I was trying to introduce in this part is that we want to try to recycle parts of these electronic wastes and try to see if we can use them to rebuild new organic soil cells and basically go on and on with recycling here. If you look a bit more closely at the organic soil cell architecture, you're usually using indium tin oxide substrates, which are quite expensive, but they don't degrade very rapidly. They're generally coated with a zinc oxide layer, which is used to modify the work function of indium tin oxide here. And then you have the active layer, which is deposited by solution process. So like I was saying, inkjet printing, spraying or spin coating. And then you have metal electrodes that are either evaporated or also deposited by solution process. Now, if you look at this architecture here, you have one part that is very expensive and that doesn't degrade. And on the other hand, you have one part that is very cheap and that degrades quickly. So what we try to check actually is if we could remove this part that degrades from the devices that reach the end of their lifetime and recover this ITO zinc oxide substrates that are the most expensive parts of the soil cell. It's actually very easy because the active layer is soluble in organic solvents. So for example, here as a proof of concept, we use two materials that are very well known active layers. So PBDBT, ITIC, the molecular structures are here. And with the same device architecture as I was showing you before, what we tried to do was to deposit these two materials as a thin film on the substrate coated with metal electrodes, and then these devices work as organic soil cells, and once they reach the end of their lifetime, we sonicate them into dichlorobenzene to remove this active layer here, so the dark blue one. And by doing so, we also remove at the same time the top metal electrodes, because you can just simply by lifting this part, you remove also the other part. If you look here at the absorption spectra, so light absorption spectra of these materials, the dark line, sorry, the black line that is in the background here is the substrate before you deposit anything on top of it. The blue line is when you deposit these materials on top of it. And the red line is when you remove these materials by sonication in dichlorobenzene. As you can see here, the black and red lines seem to be almost perfectly overlapped. So it means that we were actually, from macroscopic point of view, we were able to remove these two materials from the ITO zinc oxide surface. Now, to check if this is enough to recycle or to have a proper recycling of the ITO zinc oxide, we need to fabricate new devices, again, soil cells, and see if they work as well as the reference ones. So before going into this, I'm going to briefly introduce how we test the organic soil cells, because I think most people are not really familiar with this. So what we do is we measure the JV characteristics of the devices under simulated sunlight. And there are four main parameters that are generally taken into account when you think about soil cells in general. But we focus on the short circuit current density that you can see here. So it's the current density that you get at zero applied voltage, the open circuit voltage, which is the voltage that you get at zero current, and the maximum power conversion efficiency and field factor, which tells you how efficiently you can collect your charges once they're generated. So usually VOC depends mostly on the active materials, but here you will see that it has a certain importance because it is also influenced by how efficiently you can collect your charges and the number of defects in your electrodes. So before anything else, we should compare what happens to these substrates when they're recycled just by sonication. So you can see the results here. The reference device gives a power conversion efficiency around 8.7%. But when you just remove the active layer with dichlorobenzene and reuse these substrates to fabricate new devices, you have a large loss in power conversion efficiency. So you go from 8.7 to 4%. The thing is, just by simply annealing these substrates here for 200 at 200 degrees for 30 minutes, you can actually recover most of your power conversion efficiency. So you have some solvent that is probably left in the zinc oxide layer, which impedes the proper electron collection in your devices. So if you anneal, you dry your layer, and then you can recover your properties, basically. So just by annealing, you improve your power conversion efficiency from 4% to 7.1%. Of course, these 7.1% are still quite far away from the reference devices. So there is a need to do something else. And what we tried to do was to do an additional step of surface cleaning, which is a process that is conventionally used in all kinds of electronics. And if you think about the conventional sequence for surface cleaning in electronics, you use acetone, a surfactant, and water step, and then isopropanol, and hot isopropanol, actually, most of the time. So we tried to see if all these steps were necessary, first of all, and if we could recover most of our photovoltaic properties by using this kind of surface cleaning sequence. So remember that when we just annealed the zinc oxide layers, or the ITO zinc oxide substrates, we only got 7.1% of power conversion efficiency. If you use a surface cleaning step with acetone, you get to 8.2%. If you use acetone and surfactant, you get back to around 8.7%. And if you use an additional step with isopropanol, you also get 8.7%. So from these results, we can say that we recovered 99% of the power conversion efficiency of reference devices with our recycled ITO zinc oxide substrates. Now, to see if we can do this multiple times, we try to check it with these two sequences here, because these are the ones that give us pretty much the same power conversion efficiencies as the reference devices. And what we saw is that when we don't use IPA, so isopropanol, we still get around 7.9% of power conversion efficiency, even after 10 times recycling the substrate. So 10 recycling, and we still get very high power conversion efficiency. In contrast, when we use isopropanol as well, we get 5.1%, so it's a lot lower. So the one-time recycling is pretty much the same value, but if you recycle 10 times, it gets a lot lower. And we tried to check what was the problem there. So when you use isopropanol, it gradually etches basically your zinc oxide surface. And on your zinc oxide surface, you have a rippled structure that is very nice to scatter light, but it's also full of surface defects, basically. What happens with isopropanol is that you first start removing this ripple structure. So you have less light scattering, which reduces your short circuit current density, but at the same time, you also reduce your defects, so you increase the fill factor and the open circuit voltage. So by doing so, you have similar power conversion efficiency. The problem is that when you use more than one recycling, so up to 10 times recycling, your thickness of zinc oxide goes from 55 nanometers down to 20 nanometers. And then you increase the ratio of defects to surface compared to bulk. And because of this, you have a large drop in fill factor and in open circuit voltage, which results in a low power conversion efficiency. When you don't use IPA, you get very similar power conversion efficiencies everywhere. Fill factor doesn't drop so much, and neither does VOC. So the remaining issue is that we're using dichlorobenzene to recycle our substrates up to now. And dichlorobenzene is very harmful for health and the environment. So as much as possible, we should avoid the use of dichlorobenzene. So recently, we've been trying to replace dichlorobenzene, so synthetic organic solvent, with a more or less toxic and more sustainable solvent extracted from orange peels, limonene. And instead of using ultrasonication, which uses a large amount of volume of hazardous solvents, we changed this to something like rubbing the surface, so mechanical rubbing of the surface of ITO zinc oxide substrates. And we saw that using these two kind of alternative processes, we could also make very nice recycling and get power conversion efficiencies that are similar to reference solar cells. And when we recycle this 10 times, we get actually values that are higher than when we use sonication in difluorobenzene. So this is still a work in progress, but it's a great way to promote circular economy by reducing wastes like orange peels and also electronic waste. So if I summarize quickly, the organic soil cells are a very nice technology. So because this conference is about recycling, I also invite you to look at this second paper here, which is a method to fabricate thin films in a very environmentally safe and sustainable manner. What I presented here is basically the efficient and sustainable or soon to be sustainable recycling of ITO zinc oxide from the degraded devices. And in the future, we're actually looking into doing this also with possibly OLEDs or perovskite soil cells, and also seeing if we can not only recover these ITO zinc oxide substrates, but also the metal from the metal electrodes, and also do something with these degraded active layers, because even though they don't work very well from an electrical point of view, they're still active optically, so they could be recycled into something else. And of course, if you have ideas here, please feel free to share them with me during the question session afterwards, or discussion session afterwards. And finally, just a brief word on other projects that are undergoing in my laboratory. So we're also trying to make soil cells with natural dyes. So instead of using synthetic dyes extracted from either carrots or tomatoes, we're trying to make the whole process of organic soil cells more sustainable, and also we're trying to improve their durability. And finally, I would like to thank my team and also Professor Okada's group at UEC, also Professor Takeoka at Sophia University, all the financial support, and thank you for your attention.